Okay. Hello, my name is Eric Siegel, and I'm a product marketing engineer covering our touchscreen controller and haptic solutions brought to you by TI. And I'm here today to talk to you and give you an introductory and overview of those two technologies and what we have to offer. Let's get started. In this presentation, we're going to go over some different topics here. First, we'll start out at a very high level, look at the market overview, and then talk about the different technologies that are out there, and then really get into our offerings in terms of resistive touchscreen control, capacitive touchscreen control, and haptics solutions. So here you can see are the different applications that touch and haptics can be involved in. And I mean, really, it's touchscreens have been invading our devices all over the world. So you're seeing them everywhere, and both in resistive and capacitive form. It's now become, almost standard when you see a device and it has a screen and no buttons. It should be something you can touch. And haptics is kind of the filler onto that, where it has vibrational feedback that it gives, and maybe to acknowledge a command or transmit information of any variety. And really, they go hand in hand and can be applied in the industrial setting, consumer applications, medical, consumer electronics for sure, versus appliances over here. I mean, really, if a human touches it, it's something that can use a touchscreen controller or a haptics driver. In terms of touch and small screens, this is some of the different specific areas we call out. You see gaming, feature phones, cameras. Then you move on to medium screens. You can see tablets are getting into this, maybe some larger printers, notebook PCs. And then, of course, large and overs, usually over 12 inches in diameter. That's when you're getting into huge spaces. These may be not so much resistive or capacitive touchscreen control. They may be more optical based, because when you get into larger screen sizes, capacitive can be very expensive. Resistive may still be effective, but it depends on the application and what the end consumer is looking for. In terms of an ecosystem, this is usually what we look at and have. You start out with some sort of touch panel or display right here, which then a touch event occurs, which is then detected by the touchscreen controller, which then transmits that information to our applications processor or microcontroller of the system. And then if haptics is involved, that apps processor decides what haptic effect is the correct one, and then we'll transmit that information to the haptic driver. Now, the software for that waveform effect can either be stored on chip or the driver itself. It just depends on the topology, and we'll cover some of those different ones later today. And then the driver will then transmit that information to the actual haptic actuator, and this could be of one of the many varieties here, such as piezo or LRAs and ERMs. So in terms of our touchscreen technologies that we offer, if you didn't piece it together already, we really focus on resistive touchscreen control, capacitive touchscreen control, and haptic feedback. There are some optical solutions offered by another wing within Texas Instruments, but those are not something that are commercially available. Those are more on a strategic, case-by-case basis. Whoops. So, resistive touchscreen, just really briefly, we've been the market leader in it. We continue to have a wide variety of products available. Capacitive touch is something that is new for us, a commercially available capacitive touchscreen product. And then haptics is an emerging area that we're really seeing a lot of focus and development in. So with that, let's talk about resistive. So resistive touchscreen control is basically a very old technology, a very mature technology, and is pretty simple in terms of basic circuits, how it works. As you can see, this is the typical setup of a touchscreen controller panel for resistive, where you have two ITO films. And ITO, by the way, is indium tin oxide. And this is basically the sensor layer that's used in both resistive and capacitive. However, they're completely different technologies in terms of how they're implemented. In resistive, you have two films that are sitting on top of each other, spaced out by these microdots. And when a touch occurs, a physical deformation is created within the panel that causes a connection to touch between these two panels. And that detection creates a circuit, which then creates a voltage divider, and that's how we're able to detect the actual touch coordinates. So here again, you can see you have two voltage planes basically sitting at some reference and then a ground. And then when the touch point occurs here, in here, a voltage divider is created. And then that reference voltage is then detected by the circuitry and transmitted to our touchscreen controller, which then transmits it to the actual applications processor, microprocessor, or microcontroller of the system. Now, in terms of multiple touch detection, this is something that is new within TI's offering that we have. It's with our TSC 2020. It's a multi-touch product. Basically, with our single touch, remember, we have just one X and Y axis. So touch, we create a voltage divider in one direction and a voltage divider in the other direction. But what if we had multiple X and Y axes in detection zones? Well, that is the basic principle of operation for our multi-touch array, except instead of a 3x3, we have a 3x5. So here, one touch point occurs, but we scan and pull different areas and look for these individual touch points. So in this case, we have these 15 individual touch zones and can detect up to 15 simultaneous touches within, simultaneous touches, one within each zone. So almost like 15 mini touchscreens working together. And when you put them next to each other, you get this resistive array. So some of the key features of resistive touchscreens is that they're very cost effective. They can be activated by a stylus of any variety, so finger or gloved hands work very well with these. They're not affected by dust or water or light. On the downside, they're not as clear as capacitive touchscreen controllers. And that's due to the fact that you have to have those ITO films have to be completely covered. So you have two full layers stacked on top of each other, which obscures some of the light coming through in terms of for clarity. However, on the downside, resistive layers aren't quite as robust as capacitive because they can be damaged by sharp objects because they must be kept flexible and rigid in their space. So if you poke too hard with certain styli, it may actually poke through and damage the touchscreen itself. In terms of our products, we have a wide variety of out there right now, and some of our hero products we have selected here. So the TSC 2006 and 2004 are resistive touchscreen controllers that offer ultra-thin QFN packaging and SPI communication with I2C communication on the 2004, and these are available now today. You can sample and order them. In terms of a new device, the TSC 2020 is what I was talking about earlier with the 15 individual touch products and touch points, and it actually is available now and is being used in demos for large screen resistive tablet design. So that is an actual option there. And then releasing soon in January of 2012, we will have the TSC 2011. Now, this is a very interesting device because it's a single-touch resistive touchscreen controller with an integrated haptics driver built into it. So now you can have one device to do both of the main functions of a touch system. So here's the TSC 2020's one-page overview. You can look at more information on ti.com to find out the specifics here, but we'd like to highlight the fact that it has an I2C interface. You still get the great 10-bit ratiometric converter that we have in all of our standard resistive touchscreen controllers. And it says we currently have available a 3.5-inch screen, but as I mentioned prior to this, we have a 7 and 10-inch resistive tablet screen solution being created right now, so large screen capabilities are available. So for the TSC 2011, this is the TSC 2011. We have for the TSC 2011, we have the standard 4-wire interface for the touchscreen controller with an integrated haptics controller built into it. So we'll have a 250 milliamp output for QFN suitable for eccentric rotating masses, or ERMs, and linear resonant actuators, or LRAs. One of the key things about this device, aside from its integration, is that it offers it can operate at 1.2 volts. So as low as one battery cell to have your entire solution running and work very well. Another key feature is that it has, or key benefit is that it has 4 built-in waveforms into the device. So as a benefit to you, you can put this device on and have royalty-free waveforms that you can use right from the get-go, rather than having to spend time and develop your own or obtain your own from a third-party vendor. Okay, now we can talk about our capacitive touchscreen controller story. So first off, the basics of capacitive touchscreen controller theory. So in general, you have two parallel plates that become capacitors. And that capacitance can be changed when you introduce your finger into it or any other capacitive material. And it is that change in capacitance which is detected by our microcontroller or touchscreen controller or whatever have you for your touchscreen controller methodology, and is then notified to the main processor of the system, and then the changes are handled accordingly. So this is the stack up of the capacitive touchscreen controller setup, very different than the resistive. Here we have safety glass on top, which allows for a very robust and stable touch environment that people are used to versus the flimsier feeling that you get with resistive. The ITO patterns in this case are stacked and sit on top of either glass or PET or some sort of insulator, basically, or isolator, sorry, not insulator, and allows them to interact with each other. And then, of course, you have an air gap to space from the LCD because the LCD injects noise into your system, so you need to have some distance between it. So here's an actual picture of what it looks like. So you have your ITO here, and then your flex circuitry here, where your touchscreen controller will sit, the LCD controller on a separate line. Very simple functional diagram. Now, here's where the ITO differs significantly from a resistive touchscreen controller. Typically, you would have, in some systems, 2 layers of ITO. Now, there are some instances out there with just a single layer ITO, but in general, you have 2 layers of ITO and 2 patterns that are like 50% 50% filled out, as indicated here, much like a checkerboard. So when these 2 layers are overlaid, as is in here, the third picture, you get 1 full layer of ITO. So this is where you get, 50% difference of resistive versus capacitive. This causes the difference in the clarity of the screen itself. So here we just kind of show you stack up next to stack up, right? You have glass, ITO, etc., and then you have the flexible film for your ITO for resistive versus projected capacitive. So how do we actually find the number of fingers being touched on a capacitive touchscreen controller? In a resistive, we had just a single point of contact to make things, simple and easy with the voltage divider. However, with capacitive, it's very easy to implement multi-touch, but how do you actually detect that? First off, let's talk about what exactly is multi-touch. I'll tell you, it's the ability to have a peripheral work simultaneously with more than one input at a time. And this is not something new. It's been around for a long time. I mean, you have pianos, you have typewriters, you have Control, Alt, Delete. It's a concept that's been around, and it was not created by the iPhone, just so you know. But it was definitely popularized in capacitive touchscreen control by the iPhone. I'll give it that. So how do you detect multi-touch? Well, really, in a projective capacitive system, you need to leverage 2 key features, and that is self-capacitance and mutual capacitance. Now, self-capacitance is the capacitance of one ITO column or row, and it's with respect to itself to ground. And mutual capacitance is the capacitance of the interaction between those rows and columns. Now, what do I mean by that? Typically, capacitive touchscreen controllers are set up with an array of rows and columns. So in this case, we have a 10 by 15 array of rows and columns. So these will overlay each other, and self-capacitance is used to detect just initial changes in capacitance. Initial touch points. So you may detect, a touch occurred in this region or this region, but you don't know exactly where it is. That is where mutual capacitance comes in. So with just self-capacitance, we would do 1 scan per line, and that would be 25 scans. It's very easy, quick, and a high signal-to-noise ratio, and works with up to 2 fingers only. Because when you get more than 2 fingers, you won't know exactly if you're ghosting or not. But this may not be a problem if you're trying to do just simple gesture technology, such as pinching and pulling, or zooming, or rotations, or something like that. However, if you want to get more refinement, you need to have a special technique. You have to leverage mutual capacitance. So when you do independent sensors, you have mutual capacitance leveraged over here, and you look for the interaction. So now, instead of just 10 by 15 with 25 scans, we actually have 150 scans. This becomes a little bit more difficult in terms of routing, and because you're making a more complicated system, but overall, it allows you to have the refinement that you're looking for multi-touch systems. So in this case, what we have is one touch point that's detected, and then it's detected here, and then we can see that by driving a row, we can detect, oh, look, there's an actual gesture that's occurring here, and that some sort of, more data points are being sent to your touchscreen controller to indicate that the gesture is going. However, it is on your controller or applications processor to actually decide if it is a gesture and what should be done. So now, in this case, we have basically, again, X and Y detection with multiple fingers, and the initial scan is done with the columns, which detects these different touch points, but then the rows are driven with a voltage, and then it isolates through the the mutual capacitance to detect each individual touch point. Now, when you get into larger objects on a device, that's when you have to have gesture recognition of object detection or object avoidance, and that makes it a much more complicated system. That's where you need some sort of external circuitry to help you with detection or rejection, as the case may be. That topic isn't really covered so much in this presentation. It's left for further classes. So in general, when you look at capacitive touch, the key features are that it's very durable, resistant to scratches versus the resistive touch controllers. You don't have to actually touch it in certain cases, so that's what I mean by less touch pressure. And it can compensate to surface contaminants. So even if there are some surface contaminants on there, depending on your system, you can work around them. But in some cases, there are issues with water droplets causing problems, or oil or surface or contaminants of something. And then, of course, the superior optical clarity, brighter displays, and less surface reflection due to the less use of ITO, we'll say. Now, of course, with the negative side, when it says must be touched by a finger, what we mean by that is, it has to be a conductive material. It cannot be a non-conductive input, unlike a resistive, where you can have any sort of stylus that you would like, or you can work with a gloved finger very easily. In terms of our product line, here is what we can show you. Releasing in January, we'll have the TSC 3060, and this is a 16 capacitive channel device that's really suitable for up to 3.2-inch screens. It can detect up to 4 touches and a 1.2 millisecond full panel scan. It'll be coming in a QFN package, and we do have some demos available right now. Future generations will be, enhancements on this 3000 family, where we'll have greater than 30 channels, up to 5.9-inch screens, and we'll have more information on that in February and third quarter of next year. And then future devices will be the 4000 family and the 5000 family. But these will be, basically tiered family support for mid and larger screen solutions. Here's the TSC 3060. Here's the TSC 3060 one-page overview. More information for this product can be found on ti.com. But in general, it's a 16-channel device, so a 10 by 6 array, which means we'll have 60 nodes. It'll be available in the 4x4 QFN package, and will be available in January of 2012. It's capable of detecting up to 4 simultaneous touch points at the same time. One thing to mention is that this product will have an array of ITO options available, and it will be one of which will be TI's proprietary true single-layer multi-touch capability function, ITO. So for those customers that are looking to use a single-layer ITO, we will have a solution available for them. So now we can talk a little bit more about the capacitive system itself, and maybe just look at some of the things that are concerns and things to be aware of. In general, this is a good system design. Typically, you have your touchscreen controller in the center, and it can be connected to your ITO and LCD, and in some cases, it'll have touch button capabilities. In our case, with the TSC 3060, it's going to be either or kind of deal, but traditionally, it will be the ITO with LCD stack up. This is then connected through a flex board to your host CPU, host processor, which could be a microcontroller or a microprocessor. But we'll then have some sort of, if it's a microprocessor DSP, it'll have some sort of flash on the outside. It'll be running at 1.8 or 3.3 volts. So in terms of integration, you have your ITO stack up on your LCD, or you have your true single layer stack up on your top of your LCD. It's one or the other. But the classic two layers, some of the patterns you'll see are diamond bar, enhanced bar. The LCD itself, you can have just basically AC DCOM or DC DCOM, and just really means, do you want to have something with, noise on top, a more noisy, cheaper solution, or a less noisy, more expensive solution. Your ITO, you're going to have just different types of stack ups. So with the true single layer stack up, you have just one layer that's right there. And then, the things about integration is that you can see, will this device be directly laminated on top of the LCD? Will it be an air gap? Is there going to be a shield or shieldless? All considerations that you need to be aware of when dealing with your ITO and LCD and touchscreen controller design. So all these things get integrated in. So our solution is compatible with our multiple stack ups and sensors. We'll have, obviously, our patterns available for options. And then we have a working partnership with a lot of ITO manufacturers and panel manufacturers and sensor builders. So in terms of noise immunity, our touchscreen controller is basically integrated with, basically we're leveraging TI's very long and historic excellence in analog, and have integrated our own personalized filters into the processor, into the controller itself. So we basically have an analog engine with a mixed set of analog filters, and then some digital filters here on the front end, clamp filter, IR filter, and a moving average filter. So these filters can be turned on or off to suit your needs and get the right amount of processing and power performance that you're looking for. We feel this is going to be a key differentiator in our device, as it will not have a microcontroller embedded into it, whereas most controllers on the market today, or some leading solutions on the market today, have an integrated microcontroller to handle a lot of this filtering in software. We're actually doing it in hardware. In terms of accuracy estimation, here we can show you that a vast majority of our error or linearity issues are within less than a millimeter of detection. So, that's extremely accurate. You can see the vast majority of it is within half a millimeter. We have very good linearity. And power consumption. This is actually a really great graph because it shows here the different power levels that we're working with. This is under typical operation, but you can see less than 5 microwatts in terms of just the deep sleep. So no scans, nothing going on. Then when we're monitoring at 100 hertz, we move up to 86 microwatts. When a touch detection occurs, we're looking at 5.6 milliwatts of power consumption. Now, the thing is, if it's 1 touch or 4 touches, it's the same amount of power consumption. So really, it's a very power-efficient device, as you can see. And this scan rate is really going at 1.4 kilohertz rescan rate. So you can see it's an extremely fast device to get the full panel scan going on. In terms of low power, so typically we kind of alluded to this just a second ago, but you can see that whereas some competitors are really around 2 milliamps, we're in the 15 microamp region of the world in terms of current consumption and just typical monitoring rates. So this device is really power efficient and extremely fast, and a lot of that has to do with the fact that we are not including a microcontroller in it, because we are going to give you exactly what you need, not more, not less. So in terms of sample rate and scan rate, because we'll have a leaner machine, we'll be able to scan and sample very quickly. very first touch latency, as we showed in the previous graphs. So this is something that is also very good to be aware of, and that's the row versus channel count and how that translates into resolution. So this is the first order equation, which will allow you to kind of get a rough estimate in terms of how big a screen you can support with specific rows and columns and the pitches of those rows and columns. And what we mean by pitch is when you look at the ITO, how it's stacked up and everything, the distance between sensors is the pitch. So if you think of it, the best way I can talk about it is, we have 10 rows and 6 columns. So that's 60 nodes. Well, think about if you had a picture you were looking at and you had 60 pixels. At the right resolution, everything will look fine. But if you scale those pixels up and make them larger than they need to be, your picture may not look the exact same when you're at that same distance. You may need to move it back to get it in the right aspect ratio. In which case, you could still have a functioning device, but it may not be exactly what you were hoping for with resolution. So with 10 rows and 6 columns, typically a 5 and 7 millimeter pitch is the actual industry standard at the moment. Of course, we are seeing trends that is indicating that smaller is becoming a demand out there. But with 5 and 7 millimeters, you can see you get a 5.8 and 8.1 millimeter screen size, which roughly translates to a 2.3 and 3.2 inch screen. Now, when you're dealing with finger separation, what we mean by that is basically how close can two fingers get before they're perceived as one. And typically, just a rule of thumb, it's twice the pitch. So in this case, 10 and 14 millimeter finger separation. These are things that you need to be considering when you're designing your touchscreen system to make sure that you're accurately representing what you're hoping for your end product. So here we just kind of compare resistive next to capacitive. From a transparency, obviously capacitive wins out. Both products are able to do single and multi-touch. Resolution, the touchscreen controller for resistive is actually higher resolution because that resolution is set by the number of bits on your ADC versus the capacitive, which is set by the number of channels. The speed, the resistive is actually faster because it's just voltage-based versus looking for changes in capacitance. Both require contact. Capacitive, you can hover somewhat, but for the most part you do. Input-wise, with resistive you can use anything, whereas capacitive, you need to have a capacitive material or conductive material. Cost-wise, resistive is fairly cheap, and capacitive is 2 to 3 times that of resistive. And durability-wise, the capacitive is very good with its safety glass on top and longevity of product. Power consumption, resistive is significantly lower just because it's not constantly having to pull with capacitive. And then in terms of environmental sensitivity, the resistive is fairly resistive, and the capacitive is in some cases it just depends on your implementation of the product.